Hi, Tom the Professor here. I thought I'd start a series of videos where I solve a random introductory level physics problem. I'll show you a method and format you can use to solve any of these word problems with make them a little bit easier. So since this is the first episode, let's get started. Okay, since this is the first episode, I thought I'd give you a quick rundown of the method I'm going to be using. If you want more information about this method, there is a course available. It's free. I'll leave a link in the description. It's called Problem Solving in Introductory Physics. Now, when you boil introductory physics down to its very basic surface level, all you're doing is the scientific method. I use a 4-step method for that: observation, theory, do an experiment, and test the theory, and then report the results. We can extend this to problem solving very easily. When we ask the questions, what do they know and what do they need to find, we're doing observation. Here we're going to collect all the information the problem gives us so that we don't have to keep reading the text over and over again. When we get to the possible ways to solve the problem, that's where the theory comes in. We're going to come up with a possible solution. We don't need a complete solution at this point, just a couple of steps to get us started. When we do the testing, the theory, the experiment part, that's where we solve the problem. This is the only place the math really comes in. And so that seems to simplify it when you point that out to the students. There's only one step that we have to do all the math in. And then the easiest step is, what's the answer? That's reporting the results. Again, if you want more information on that, there's a link in the description for a free course. There's a template there that you can use to fill in answering each of those questions. Now again, this is just going to be a random problem from a textbook that I happen to have lying around. And this time I chose a problem from a book from Merrell, Physics Principles and Problems. It's an older textbook, but it's got some great problems in it, so I just thought I'd start here. It's from Chapter 9, Momentum and its Conservation, and it's problem number 10. I'll put the text of the problem up here on the screen, but I'm not going to read it because I find that boring and I don't want to watch it again anyway. If you want to stop the video here and copy down the text so that you can work the problem along with me, go ahead and do so now. Okay, now we have some numbers that pop up right here, and what we're going to do is we're going to start out with our observation. What do we know? Okay, we've got rockets that produce a thrust of 35 newtons. That will be a force. We have a 72,000 kilogram value here. That's a mass, the mass of the satellite. And we're going to be changing the velocity by 63 centimeters each second. Okay, that's all good information we should write down. So let's collect that information here. Net force 35 newtons, mass of 72,000 kilograms, and a change in velocity of 63 centimeters per second. Now when we do calculations with velocities, we want them in meters per second. So let's go ahead and change the units here right now before we get started with anything else. The next step, of course, is going to be, what do we need to find? Okay, and it comes in the last sentence in this particular problem. How long should the rockets be fired in order to change the velocity by that amount? So let's copy that information down as well. How long should the rocket fire? It's a time that we'll be measuring in seconds. Now, since this problem comes from the momentum chapter, we might start with momentum. Okay, momentum is mass times velocity. The mass isn't going to change in this problem, but the velocity is. If you are using a textbook that starts with one-dimensional motion and describes speed, speed and velocity are interchangeable at that point. Velocity only becomes a little different when you're working in multiple directions where you have a direction associated with the speed. The other idea that comes out at the beginning of this chapter is impulse. It's how we relate momentum with force. And you notice in this problem we have a force listed that the rockets will produce, and so we'll probably need impulse here. So let's write it down. Impulse is force times the time the force is being applied to your object. the big idea in this part of the chapter is impulse is the change in momentum, and that's where we're going to get our first equation. So we'll write down the impulse, force times time, and that's going to equal the change in the momentum, the mass times the speed. Again, the mass isn't changing in this particular problem because we're using an ideal sort of setting. In reality, every time the rockets fire, it does change the mass of the rocket. That's where the force actually comes from. But we're not going to worry about the mass changing here. So we can adjust that where that changes when we need to. Now we're looking for the time the rockets will fire. So let's solve the equation for time, and we get this equation here. Okay, let's write that down in our possible solution section of our thing here. We've got the impulse as the change in momentum, solve that for time, and then we can go ahead and fill in the appropriate numbers here. 72,000 kilograms for the mass. The change in the speed is 0.63 meters per second. And then we'll divide by the force of 35 newtons, which already gets us to the final answer, the last step in our method. The time is 1,296 seconds, or 21.6 minutes. Now, if we didn't know that this was from the momentum chapter, I may or may not tell you what chapter these come from. Is there another way of solving this? You will find that in most physics problems, there is always more than one way. Just for fun one day, we were working I forget what type of problem it was, but I knew three possible solutions off the top of my head, so I took the students through those 3 solutions and then said, are there any more? And the students were able to come up with a 4th different way of solving the same problem. It's kind of fun if you're into that sort of thing. These were engineers, so yeah, they're into that thing. But anyway, can we go back to a more general starting point? Do we need to know momentum and impulse and all that sort of stuff? Well, no, not really, because we can get the answer a different way. One of the basic principles in introductory physics is going to be Newton's laws of motion, right? Newton's first law, Newton's second law, Newton's third law, and then how those relate to energy later on. The most general one is Newton's second law, so let's start there. The net force is the mass times the acceleration. I say this is the most general one because if you put an acceleration in a 0 acceleration, that gives you Newton's first law, where the net force is equal to 0, meaning your object is in equilibrium, and so on and so on. Okay, so let's start with the net force here. This equation, Newton's second law, doesn't include time specifically, which we know we have to solve for. So we'll need to come up with a way of solving that. And that's going to be through the acceleration. We're already given the force. We're already given the mass. The only thing in this equation we don't know is the acceleration. So let's go ahead and solve for it. We can throw in the 35 newtons. We can throw in the 72,000 kilograms. And we get an acceleration that I'm going to list right here. All right. Now, that acceleration does relate to velocity and time, as you would expect. Acceleration is the change in velocity divided by the time it takes to change that velocity. So let's write down that equation. And then we'll solve for the time because that's what we want in this problem. Right? So the change in velocity, 0.63 meters per second again. The acceleration is the number I just found. And when we do this calculation for time, we get the same 1,296 seconds, or 21.6 minutes. So again, there's more than one way to solve almost every problem in physics. So I encourage you to look for those. It's great to do. It's a great job, a great exercise to do. And it gets you thinking in the way we should be thinking about science, where there's not always one solution to every problem. Well, that's it for this particular video. Thank you for watching all the way to the end. I ask you to like and subscribe if you liked the video and want to see more. If you want to contact me, I have social media set up at Facebook and Twitter. The link is here on the screen now. I also have a lot of this information in a blog at tomteacheспhysics.com, where I write about physics in everyday life, how to teach introductory physics, and just answering some questions that sometimes pop up on Twitter and other ideas that I randomly have throughout the day. I will see you next time.